Okay.
What was your question?
It's recording. Awesome. Great. So everybody, let's start. Are we good? Yeah? Great. Okay, so we'll start. Yesterday we were doing on Wednesday we were doing the Euclidean algorithm. I'll post the proof of that. I mean, it's a slightly long proof. I'll post it. Now we can move on to something else. But is it clear how you can find two integers u and v such that au plus bv is equal to gcd? It's not a complicated thing. Most likely on your midterm or in your final you have one question like that. You know, just to test you, to see that you were following in the class and do the homework. Easy question, easy points. Do get it, like understand. Okay? So great, awesome. Now we move on to the fundamental theorem of arithmetic. Okay, so before I start the proof, suppose I give you a number, let's say 12. Can you break it further? Suppose I give you a number, 12. Can you break it down further?
Yeah.
Break it down in what sense?
2 times 3.
It's, well, how do you break it down? Let's start. Is 2 a divisor of 12?
Yes.
2, so it's 2 times 6. Can you break the 6 down? 2, can you break it further?
Yeah.
2, no. 6, can you break it further?
Yeah.
In what?
3 times
2 times 2 times 3. Great. Now, I want to say, okay, I don't want to start with 2 times 3. I just want 12 is 3 times 4. Can you break 3 further?
No.
4, can you break it further?
Yeah.
How can you break it?
2 times
3. Okay, so this is 2 times 2 times 3. Now, 2 and 3, what's the property that they have? They are prime numbers, right? Now, did you notice that these primes are the same? Did they change from each other?
No.
No. Now pick another number, let's say 18. How do you break it down? Let's start. Is 2 a divisor of 18? Let's break it down 9 times 2. Then can you break the 9 further?
Yeah.
So how can you break it? 3 times 3 times 2. So it's 2 times 3 times 3. Can you break the 18 further? Let's see, how can you do it? Is 3 a divisor of 18?
Yes.
6 times 3, let's say, or 3 times 6. And what is 6 equal to? This is 3 times 3 times 2. Now notice these are the same. So any number that is, say, strictly bigger than 2 can be broken uniquely, in a unique way, into primes. Do you see that? Yeah? So let's prove this theorem. It's called the fundamental theorem of arithmetic. I think my handwriting on that is arithmetic. This looks like an N. Arithmetic. Okay. Let's prove this. I mean, before I prove this, I need a small lemma. Okay, everybody, please, I need you to be calm, okay? So let P be a prime number. And let AB be in Z. If P divides AB, then P divides A, or P divides P. Okay? Let's prove this. The proof of this theorem uses Bézout's lemma, or Bézout's identity. So how do you prove it? So I have that P divides AB. Well, if P divides A, I need to show that P divides A or P divides B, right? This is what I need to show. Now, if P divides A, then the theorem holds, right? Clearly, if P divides A, then the theorem holds. Now, if P does not divide A, we need to show that P divides B. Isn't that right? Are we good here? Everybody? Stuff. Are we good? Is it clear? Any question on that? Okay, so if P doesn't divide A, what can I say about the GCD of A and P? Let's have a look. If P, well, GCD of P and A divides P, agree? The GCD of two numbers divides each of the two numbers, right? Agree? Everybody? So, the GCD of AP is equal to 1 or is equal to P, since P is prime. If P is prime, what are its two possible divisors? Its two possible positive divisors, strictly positive divisor. It's 1 or P. Are we all following? Any question on this? Please raise your hand. It's important. That all good? Yeah? Okay. So GCD AP is equal to 1. Why is that? If GCD of AP is equal to P, is equal to P, sorry, then P would divide A. You agree or not? Everybody, if the GCD is P, since the GCD of AP divides A, then P would divide A. Which is a contradiction to our assumption. Contradiction to P does not divide A. Great. Now, if GCD of A and P is equal to 1, how can I write the GCD? I can write it as a linear combination of A and P. Then, there exists U, V, and Z such that AU plus BP is equal to GCD of AP is equal to 1. Agree or not? This is by Jesus' lemma. I can write the GCD as a linear combination of, oh, not P, that's VP, sorry. VP is equal to 1. So far, so good. Any questions so far? Are we good? Great. So, what do I do here? I need to show that P divides B. Did the B appear anywhere here? Did I use a B? Did I use my B here? No. So let me just multiply these two things by B. So B times AU plus VP is equal to B. Agree or not? B times 1 is equal to B. Okay, so I have AB times U plus VP is equal to B.
If you're missing a B.
What am I missing?
When you just
oh yeah, sorry, yes. VAU plus BVP is equal to B. Agree or not? I claim that this shows that P divides B. Why is that? Anyone can help? Someone else? Someone else? people who did not, whose voice I never heard before? No? Yeah, since you were the first, go ahead.
Well, AU is an integer. Yeah, AU is an integer. So you have that B times an integer plus, and B is also an integer. So you go to like B times an integer plus B times an integer is equal to B, which means that the GCD of BP is equal to B.
Ah,
No.
this means that the GCD of BP divides B, right? It's a good approach, but there's an easier way. What hypothesis? But it's a good try. It's a very good way of thinking. Okay, now you say okay that the GCD of B and P is equal to B, but it doesn't say that. Bezout's theorem is one way. It says that AU plus BB is equal to the GCD of AB. Unless this B is 1, right? But anyways, let's not worry about that. But there is an assumption we did not use. What is the assumption we did not use yet? That P divides, oh well, where's the statement of theorem? P divides AB. Agree? P divides AB. This implies that P divides AB times U. Agree? Because U is an integer, as you said. Right? P divides VP, obviously. Well, P divides P. This implies that P divides BVP. And this implies that P divides ABU plus BVP is equal to. This argument is very important. Arguments like that are very, very, very important, and they're gonna follow us until the end of the course. Okay? Is it clear? Yes, sir. Oh, this is by assumption. P divides AB, then P will divide A or P divides P. So P divides, let's say, pick P equal to 2, say, and A is equal to 3, and B is equal to 4. So P divides AB, right? But P does not divide A. Good? Are we good here? Very good. Now corollary, I said corollary. Of course, if P is not prime, then this is not true. I'll let you think of an example. Easy example, don't think too hard. If P is not prime, then this theorem is not true.
P
Okay.
equals to 4, A and B will equal to 2.
One way, very good. Yeah, if P is 4, A and B is 2, P divides AB, and
P does not divide
P
A,
doesn't
nor does
divide
B.
A, and does not divide B. Very good. Prototypical example. P squared is P times P. Yeah. Typical example. P squared is P times P. Anyways, great. Okay, corollary. I'll leave you I'll leave you to prove it as an exercise. Let A1, A and B integers, and P be a prime number. If P divides A1 times AN, then P divides AI for some I. Basically what it's saying, if you have a prime number dividing a product, then it must divide at least one terms of the product, one of the factors. Okay, great, awesome. Great. Now we move on to prove the fundamental theorem of arithmetic. Now before I I prove it, I need a small thing. It's called strong induction. And it's just basically a form of induction. It's a way of proving statements about integers. So let Pn be a statement or a proposition or anything. Okay? Suppose that P1 is true. If n is an n, the second property, if n is an n, this is the difference between that and induction. P1, P2, up to Pn are true, implies Pn plus 1 is true. Then Pn is true for all n and n. Okay? If you're convinced with induction, then you must be convinced with this. Okay, this is a stronger statement than induction. It's stronger, right? You're making an assumption that not only the previous, when you do the induction hypothesis, not only does the previous one hold, but all the previous ones hold. Okay? Now, the magic is that this is equivalent to regular induction. These two things are equivalent. Yeah?
Because induction already proves the ones before, so with that on the induction, we
Induction
only use
proves
the
that.
one.
You can
No.
prove that by induction. And
No.
with that, you can prove the well-ordering principle.
No, but like no, on normal induction, which is more weak induction, you only need the previous
Yeah,
one.
exactly.
So,
But you
but
could-
all the ones before already worked, it's just that you didn't need them. But for strong induction,
Well,
you're likely to do.
This
need
one,
them.
you prove it by induction.
Yes. No, you still prove it. It's an induction as well. I just mean
Yeah.
that for a weaker induction, you don't need the
You
previous
don't need
ones,
it.
even though they are true as well.
Exactly, exactly. Even though they are true, then, but you don't need them to prove the statement.
Yes.
I mean, recurrent installation of second order, you need strong induction. Yes, sir.
Why are the arrows only in one way?
What is it in one way?
Two. Wouldn't one side apply the other?
Here?
Yeah.
No, if these ones are true, then this is the statement.
But isn't like doesn't it go both ways? If Pn plus 1 is true?
No, I don't think so.
Not
No,
necessarily.
I don't think so.
That's not part of the proof.
Okay.
But
Guys,
part 1 says like isn't induction just part 1 that the right side and then 3?
regular induction is that this.
Yeah.
Pn is true implies Pn plus 1 is true. Okay? Strong induction, you assume all the previous ones are true. Okay? If you're convinced with induction, then you must be convinced with this. This is a stronger statement than induction. Right? Anyways, okay. Well, it's not a stronger statement. I mean, it's a, yeah, anyways. Stronger, weaker. I mean, they're all equivalent to each other at the end. Great. Now let's prove the fundamental theorem of arithmetic. So the first of all, fundamental theorem of arithmetic. Let n be bigger than 2, an integer. Then, there are two statements. There exists. So excuse my notation here. This is not going to be the most efficient notation, but let's see, L and N, but I'll try to avoid using P's because I need the P's later on. There exist L and N and x1 up to xl that are prime. With N is equal to x1 up to xl, and what? This is the first statement. 2. Suppose that N is equal to x1 up to xn, where x1 is less or equal to xl. Basically, so you have N is equal to 18. This is going to be 2 times 3 times 3. Okay, you arrange them in ascending order. This is what this means. Where x1, xn are primes. Or should I change? Let me change them. Should I? Yeah. I mean, you know, the proof is x1, xl are primes. Then, if n is equal to y1 up to yt, where y1 is less than y2 is less than yt, and y1 up to yt are prime numbers, then t is equal to L and y1 is equal to x1, y2 is equal to x2, and so on, and yt. Okay? Do you understand this statement? This one is a bit complicated. It just says that any numbers can be factored uniquely into product of prime numbers. Okay? Any number, any integer n strictly bigger than 2. Any integer n strictly bigger or equal to 2 can be factored uniquely into a product of prime numbers. Okay? This is what this statement says. Yes?
Just for the upper board, the last line.
And y1 up to yt are prime, then t is equal to L and y1 is equal to x1, y2 is equal to x2, up until, oh man, I cannot write anymore here, up until yt is equal to xt. Okay? This is what it said, that the prime decomposition is unique. Great, let's prove this. We prove this by strong induction. Let's prove the first statement. And we could do the strong induction or a well-ordering principle. Let's do a strong induction one. Prove existence. Do you want to do a strong induction? By strong induction. Okay, suppose, well, for n is equal to 2, the base case. Two is clearly 2, right? 2 is already a prime. Agree or not? Are we good? 2 is already a prime. Now, the induction step. suppose that the statement is true for all integers less than or equal to n. We need to show that this statement is true at n plus 1. N plus 1 is a product of prime numbers. Okay? Are we good? Now, if n plus 1 is prime, then we're done. Agree or not? If n plus 1 is prime, then we're done. Now, if n plus 1 is not prime, how can I write n plus 1? Yeah?
We can write it as a product of A, B, where both A and B are between like the are smaller than
yeah,
n plus
exactly.
1.
If n plus 1 is not prime, then n plus 1 can be written as n plus 1 is equal to A times B, where A is strictly bigger than 1, A and B are strictly bigger than 1, and strictly smaller than n plus 1. Agree or not? If you have a number that is not prime, you can write it as a product of two integers that are bigger than 1, strictly bigger, and strictly smaller than the number, right? So what is a number that is not prime? Let's say 6. You can write as 2 times 3. 2 is bigger than 1, smaller than 6. 3 is bigger than 1 and smaller than 6. Great, awesome. Now I can apply the induction hypothesis to AB, right? By the induction hypothesis, A can be written as A1, A2, I don't want to use M, I don't want to use M, I don't want to use L, AD, let's say, where D is an N, and A1 up to AD are prime. And B can be written as B1, B2, and is BE, where E is an N, and B1 up to BE are prime. E not being the exponential, right? It's not like E. Just a second. Okay? Basically, what is it saying? If you have n plus 1, you can break it down into two smaller numbers, right? These two smaller numbers are a product of prime numbers by the induction hypothesis. Agree? So, take the product of these two and rearrange them in ascending order. Then, n plus 1 is equal to A1 AD and B1 BE, which is a product of prime numbers. Agree or not?
It's not BG, it's BE.
BE, sir. Oops. A1, AD, B1, BE, A1, AD, B1 up to BE. So n plus 1 is a product of prime numbers. All good? Okay, of course you can rearrange them to get them in increasing or ascending order. Okay, I mean, what is saying? So let's look at, let's see. Let's look at 180. Okay? Yeah, let's look at, well, let's look at something else. Let's look at 200. Well, let's look at 100. Okay? Let me write 100 as 10 times 10. This is the induction step. N plus 1 is 10 times 10. Now this 10 can be broken into a product of primes. This is 2 times 5. And this 10 can be broken down into a product of prime. This is 2 times 5. Right? Are we good? So this 100 is a product of primes. This is how you break them up. Okay? Great. Now we prove the uniqueness. We prove uniqueness. In other words, oh well, let me finish this. Hence, by induction, every n in n bigger or equal to 2 is a product of prime numbers. Prime. What time is it?
It is 11:09.
11:01. 15 minutes we have left. We proved the uniqueness. Okay, so every number is a product of primes. I mean, you know, if it makes you feel more comfortable, this proof will not be examined in the midterm. Okay? That makes no sense. Imagine 50-minute midterm and write down a proof like that. We proved uniqueness. In other words, if n is equal to alpha 1, alpha 2, I used alpha t here, or alpha l in the first statement, alpha t.
It's first L and then T.
So alpha l, yeah,
Yeah, L.
is equal to beta 1 up to beta t, where
Why do you use those?
alpha 1, alpha l are prime with alpha 1 is less or equal to alpha 2, less or equal to alpha l, and beta 1 up to beta l are prime with beta 1 is less than beta 2, should be less than beta t. Then t is equal to l and alpha I is equal to beta I for all okay? Basically, if you can write this as a product of prime numbers satisfying these two, then satisfying these two conditions, then alpha 1 is equal to beta 1, alpha 2 is equal to beta 2, and the number of primes are equal to each other. Okay? Again, the proof is by strong induction. By strong induction. The base case is n is equal to 2. It's clear, right? It's true, right? 2 can be written uniquely as a product of prime, which is 2. Agree or not?
Yes.
Yeah. This is clear. Since 2 is equal to 2. Great. Now the induction step. Okay, suppose that the statement holds for all integers. Just for the sake of notation, I'll just 2, 3, up to n minus 1. Okay? I'll just do n minus 1 and then do n. Instead of n implies n plus 1, I'll just do n minus 1 implies n. That's okay, right? Yeah. Let n be equal to alpha 1, alpha L, beta 1, beta t, where alpha 1, alpha L are prime, with alpha 1 is less or equal to alpha 2 is less or equal to alpha L, and beta 1 are prime, the betas are prime. It's a proof with a lot of notations, but you know, are prime. I claim that alpha 1 is equal to beta 1. We'll show. Great. Are we all good? Let's try alpha 1. Well, alpha 1 divides n. Is it clear or not? N is alpha 1 times alpha 2 times alpha 3 times alpha t, alpha L. Does alpha, it's clear that alpha 1 divides n, right or no?
Yeah.
Everybody, is it clear? So alpha 1 divides beta 1, beta 2, up to beta t. Agree or not? Because n is equal to beta 1 times beta t times beta 2 up until beta t. Now, alpha 1 is prime. If a prime number divides a product of integers, what could I say about this prime number?
It divides one of them.
It divides at least one beta j. So alpha 1 divides beta j for some j in 1 up to t. Great. Okay. Now what can I say about beta j? Well, what do I have about beta j? Beta j is beta j is
It's smaller than j.
yeah, but what's the most important property about the beta j's? They are
Prime.
they are primes. If you have a number that divides a prime and this number is prime, what can you say about alpha 1 and beta j?
They're the same.
They are the same. So alpha 1 is equal to beta j, since beta j and alpha 1 are prime. Here you need the fact that alpha 1 is strictly bigger than 1, you know, to conclude this. Great! Awesome! Let's repeat the same argument. With the betas. Beta 1 divides n. Agree or not? So beta 1 divides alpha 1 up to alpha L. So beta 1 divides alpha I for some I in 1 up to L. Did I write here? Oh, alpha 1 is prime since beta 1 is prime. Great. Beta 1 divides alpha I for some I in L. So beta 1 is equal to alpha I, right? By the same argument as before. Agree or not? Alpha 1 is prime, alpha I is prime. Beta 1 divides a prime number, and beta 1 is also prime. So beta 1 must be equal to alpha I. Agree or not? Everybody, are we following?
Yeah.
Any question on this? Okay. Now I claim that this gives us that alpha 1 is beta 1. Alpha 1 is equal to beta j. Agree or not? Beta j is bigger or equal to alpha 1. To beta 1. Agree or not? Yes or no? Now beta 1 is equal to alpha I. So far so good. I'm just rewriting all the steps that I have. I'm putting it, yes?
I'm a bit confused over here. How can alpha 1 be equal to that's j? Like, how can it be equal to all of the...
No, it's for some j, it's not for all of them.
Oh,
It's equal to one of them.
okay.
Okay? Is equal, so alpha 1 divides beta j for some j. So alpha 1 is equal to this beta j. Okay, now alpha I is also bigger than alpha 1. You can squish them all together. So beta j,
Say alpha 1.
so alpha 1 is equal to beta 1. Boom. Done. When alpha 1 is equal to beta 1, then alpha 2 up to alpha L is equal to beta 1 to beta 2 up to beta t, right? I just canceled the alpha 1 and the beta 1 from here. Cancel them out. Agree or not? Can I apply the induction hypothesis here? Are these two numbers strictly smaller than n?
Yes.
Yep. My induction hypothesis L is equal to t, and alpha 2 is equal to beta 2, alpha 3 is equal to beta 3, alpha I is equal to beta I for all I and t. Okay? The theorem holds true. Okay? It's not the best proof. Again, it's how much time do we have left? We have 5 minutes left? 5 minutes. Oh, exactly. Okay. Hence my induction. Oh, by the way, the first homework is due today, and the CrowdMark is open already. Okay? If you have a problem with connecting to CrowdMark, please let me know. Okay? Should be no problem, but please let me know. And the second homework is posted. If you want to submit it early, you're free to do so. Yes, sir?
What's the late policy?
What do you mean a late
Late
policy?
policy is late. If we don't have time, whatever, like, do we use marks or just like? you're
Zero.
not-
Like, you don't hand in.
Zero.
Yeah, you don't hand in late. I don't know, is there a late policy in math or?
Sometimes you can lose 14% for MATH214, every
okay,
single
really?
day.
Okay. I don't know. I'll ask if it's a departmental
Sometimes
thing.
it's a limit of 2 days and you lose 10%. It depends. But
Yeah, so no late homework, okay? Because the graders are gonna grade. I'm not grading the homework. There are 4 graders who are grading 220 students, possibly more, right? So if you hand in on 2 days late and 3 days late and 4 days late, it's gonna be a bit difficult, okay? I mean, if you have an excuse or something like that, or a holiday or something, you know, like that, I'm very tolerant. You know, like I will definitely extend it. You know, it's not but for valid reasons. It's not like I have a lot of homework from other courses. Okay, this course is not less important as other courses, and other courses are not less important than this one. Okay, great. Okay, hence improve the state. But I think I told you the very first day of lectures that homework are going to be weekly and you're going to have something like 10 exercises, right? Like, I told you the very first day that this is, that you have a lot. Okay, so let's just prove some, yes?
for the exercises that require some prerequisites,
Yeah.
are those still likely to be graded as well?
Yeah,
Oh,
yeah. Yeah,
No.
yeah.
oh
Definitely.
man.
So what are the prerequisites? It's linear algebra, right?
Yeah.
Okay, so let me finish with some statements, some exercises. Okay, these are very good. These are very good questions on the midterm or on anything like that, you know. So please, like, do them. So let AB, guys, A, please, B in Z. Then GCD AB is equal to 1 if and only if there exists U, V, and Z such that AU plus BB is equal to 1. Then, you know, I just need you for 2 more minutes after the bell, after 25, just to ask a few questions. It's not about the course, well, it's about the course, but I'm not going to do anything. 2. Yeah. If P is a prime number, and P divides AB, no, what am I saying? No.
You already did that.
Yeah, I already did this one. Let AB be C, B, and Z with A non-zero. If GCD AC is equal to 1 and A divides BC, then A divides B. 3, every n in n, this is why I did not use P before, can be written uniquely. We'll show that, I mean, this should be obvious. Show that every n in n, n bigger or equal to 2, can be written uniquely as